Okay, welcome to this example problem of an application of Bernoulli's equation to the draining of a tank. This is a good example problem because it's one that Bernoulli's equation actually works for in a wide range of conditions, but also there are cases where it can stop and make you think and question those assumptions, as you should every time you use a set of equations. So we'll discuss some of those points as we work through that, and also some of the complexities and thought processes that go into solving it. So the first thing to look at is, of course, the problem statement. And here we have a cylindrical tank that has the same cross-sectional area in the vertical direction. And we have that as AT as the cross-sectional area of the tank. And in this case, it's uniform. And we have then a hole that's located a distance capital H below the free surface position, at least at the initial starting point. And at t equals 0, we open the hole and allow the water to flow out, and it comes out in a parabolic arc, and the flow draining the tank, and the interface, the free surface, settles as it goes down. We're also told here that we're asked to find how long does it take for the tank to empty, and that we may assume that this area of the tank divided by area of the exit should be much greater than 1. So we have a large disparity in the areas here between the exit area and the cross-sectional area of the tank. That'll show to be important in just a second. Okay, so the first thing we should do is check our assumptions for Bernoulli's equations. And of course, as you'll hopefully remember, the Bernoulli's equation has 4 distinct restrictions to it that are listed here. The first is that the flow has to be incompressible. And what that implies, of course, is that the density is equal to a constant. We're here working with a liquid in this case, and liquids are, especially something like water, is known to be highly incompressible. And so this is in all likelihood a quite good assumption. The second one is that the flow should be inviscid. Okay, now this is kind of a tough one to figure out. There are cases where this is reasonable, and there's cases where this doesn't work quite so well. It depends on the viscosity of the fluid, the size of the tank and holes, and just the conditions of the problem. For larger tanks and most working liquids, it's reasonable, but this is something that merits further discussion, and I have another video I'm preparing that will look at this in more detail. And I've done a few experiments in my kitchen to sort of explain and illustrate that. So we'll discuss that at another time. The third assumption is that the flow has to be steady. Now, for this particular problem, that seems perplexing if you've not thought about it before, because the definition of flow being steady is that it should be invariant with time. And if you've ever pulled the plug out of a tank and watched it drain, you'll know that it's anything but steady with time. The exit velocity of that jet changes as the level in the tank drops. If I sit at a fixed point inside the tank, the velocity there also changes. And in fact, at one instant you can be inside the fluid, and as the interface passes, you will be outside of it. So what does this mean? What do we think about that? Well, technically, what you want to satisfy is, officially, it would be du dt is equal to 0 for a flow to be steady. But that, as we discussed, is technically not the case here. So instead, we want to do this approximately. We want to have du dt is approximately equal to 0. When we say approximately, we also always have to compare that to something. And namely, it should be much, much less than the other terms that contribute to Bernoulli's equation, which would be the potential head due to gravity, gh. Well, that's not quite the right units there. So if we have rho times du dt, that would be like rho gh, and it should also be less than the kinetic energy, which would be 1/2 rho v squared. And it turns out that this is a reasonable assumption, provided that those areas are much dissimilar from one another. So if the area of the exit divided by the area of the tank is much, much less than 1, it turns out that this will be a reasonably small accelerations inside there. Under these conditions, we call this quasi-steady. So that means the flow is slowly changing through time, but it doesn't have any significant temporal accelerations associated with it. We'll talk about that a little bit more in the problem as well. The fourth assumption is that this is applied along a streamline, and so we have to think about what streamline we want to apply that to. In this particular case, it's helpful if we sort of cut the tank in half and look at a cross-section of the tank. And whenever doing Bernoulli's type problems, you have to pick 2 points on your given streamline that are going to help you solve the problem. So it's most beneficial to pick points where you know something about the flow, or you're trying to find something out, since that dictates your variables. So here we know something at where the liquid is in contact with the gas. So we'll draw a streamline that goes from the free surface up here at the top, and then if you think about the flow draining in this tank, it's going to come down and eventually go out the exit. And if I pick any other point, arbitrary point in here, it would probably do something similar to that, like so. And they all end up coming out this exit here. So this streamline will start at point 1 there, and then we'll travel along that path at this one instant in time and compare that to the point at the exit and look at the energetics between those 2 points. And at this exit point, we also know what the pressure is. Now, what we're really looking for here is the velocity. So this is, we'll call this here point 1, and this here point 2 at our exit. And what we'd like to do is, if we could find the velocity at the exit, this will then, we can relate to the flow rate and relate that to the tank draining rate. And that is because everything that passes out there lowers the level in the tank. In fact, it's the conservation of mass statement, meaning area of the tank times V1 at that interface has got to be equal to the area at the exit times V2. And this is, of course, assuming that these represent average velocities at each of those cross-section. For the settling free surface inside the tank up here at point 1, that's a very good approximation, as long as no one's stirring it up vigorously. And at the exit to the jet, provided that frictional effects aren't important, that's also a reasonable thing to have. Moving on then, we want to before I forget, I just wanted to make clear, now that I've erased the slide here, that once we have the volumetric flow rate, the rate at which that free interface settles, if we mark that and let it drop a certain increment delta H over a given time delta T, taking the limit as delta T goes to 0 gives us dH dt, and this is exactly the velocity of that free surface, V1. And in fact, it's the negative of it because that velocity magnitude corresponds to a decreasing height. Remember, this coordinate direction measuring up from the exit point as our reference is h, so it will be getting smaller as the tank drains. Okay, now that we're have moved on to solving the problem here as for a preliminary discussion, the first step is to apply Bernoulli's equation between the free surface and the exit, where the free surface is 0.1 and the exit is 0.2. So writing that out, we have P1 plus 1/2 rho V1 squared plus rho G Z1 is equal to the similar terms at position 2. So now we'll walk through each one of these in turn and figure out how to simplify this. Okay, let's start first with our datum. We'll define our z equals 0 point here at the exit of the jet. This is arbitrary, so we could pick it anywhere we want, as long as we're consistent. But it is convenient, so this term will equal to 0. And shown here, I have the distance h is measured from that reference point to the local free surface. So this z1 becomes an h. Okay, we can also look at the pressures here, and we know that we have local atmospheric pressure acting on the free surface of the tank and acting over here where the jet is exiting. So here on P1, we know that that is going to be equal to P atmospheric. And over here, well, what do? It turns out that this is also equal to the atmospheric pressure. But you may ask yourself, why is that? Well, this has to do with the fact if we look at a small little slice of that jet right there at the exit, if we examine, here we know at the interface along the cylindrical surface we have atmospheric pressure acting at all points along the outside of that jet. And this flow is more or less, is largely unidirectional, and so there's not a lot of strong curvature, although there is a weak curvature. I'll talk about that in just a second. This flow in here, it turns out, is actually atmospheric all the way through it. There's nothing there basically to support the jet, and so the pressure inside there remains the same all the way across it. So this is a good take-home point. Let me just put it up here because it's important and useful. For free jets, we have that P is equal to the local atmospheric pressure. And it turns out that's generally true also if we have gas jets exiting into a gas atmosphere, liquid jets exiting into a gas atmosphere, or liquid jets exiting into a liquid atmosphere. That's generally a pretty good assumption. Okay, so we then also have here the velocity at the exit, which we're trying to calculate, so that's unknown, plus 1/2 rho v2 squared. That last term was 0. And our last one then is, what is this velocity 1/2 rho v1 squared? Well, if we want to be strict about this, what we can do is we can use our equation of conservation of mass and that assumption of it having a uniform velocity across the inlet and exit, and say again that AT times V1 is equal to AE times V2. And so we can relate this to V2 by saying V1 is simply AE over AT times V2. And so we could plug that in. So carrying this through, we could write first of all, this atmospheric pressures will cancel out, and I will have now AE over AT times V2, and these quantities get squared, times 1/2 rho plus rho GH is equal to 1/2 rho V2 squared. Okay, well, just an observation though. We could keep this, but it'll make it a little bit more cumbersome, so let's make this observation. I argue that this term is going to be very small in comparison to the other terms. And it's going to rely on that fact that we had, due to area of the exit divided by area of the tank, is much, much less than 1. So if we go back up here, let's say that DE, the diameter of the exit, is equal to 1/10 of the diameter of the tank. Well, if I take AE over AT then, that's going to be equal to DE over DT squared. And if I say that's 1/10, that's going to be equal to 1 over 100 when I square it. Now if I come down to this term, I'm going to have here AE over AT squared. So for that, AE over AT squared is equal to 1 over 10,000. So if I have 1/2 rho V1 squared, or V2 squared over here, and 1/10,000th of that over here, this is approximately equal to 0. It's negligibly small. So it's reasonable to neglect that. We don't want to needlessly complicate things we don't have to. And so then this remaining terms that are left gives us simply V2 is equal to the square root of 2GH. All right, so the astute student will recognize this, and you've seen that before in your physics and particle mechanics class, where this is exactly equal to the velocity that a point mass attains when released from rest and allowed to drop a height h with no frictional or external forces applied to it other than gravity. And this is an equivalency between the potential energy and the kinetic energy when it's conserved in a system like that. And it turns out the same is exactly true for an inviscid fluid. As there's potential energy stored in this liquid due to the height of the column of water above it that generates a pressure field. This local pressure difference then accelerates the fluid up to a velocity magnitude that converts all of that potential energy into kinetic energy. And it's the same for both a fluid as it is for a solid particle. Now if we have frictional effects or other things coming into play that put another force on there, then this can be modified. But this is a generally true result in that case. And so the interesting thing to note is it doesn't depend on rho, and it does not depend on, so the density, and it does not depend on the area of the opening. That velocity magnitude will be the same whether it's a small or a large opening. Again, this is neglecting a few other complicating factors. But that's a very powerful result. It only depends on the height of the column of liquid that's backed up behind that hole. One more note about this free jet before we leave this page, now that we got the answer we need, is you'll also notice in looking over here at this problem that this jet falls in a parabolic arc if you look at any sort of experiment or if you played around with a hose. And if you know that a parabola, even if this is tangent and comes out horizontal, there is a finite curvature at that apex. So there's a radius of curvature here, r. And so these streamlines here that I drew in this are not truly straight, but they're slightly curved. And so you'd say, well, that should have a pressure gradient then across that. Well, if we write down the equation for an inviscid flow normal to a streamline, we have here rho times v squared over r, the script r is our radius of curvature. That's equal to dp dn plus rho g. Okay, so now we know that gravity is acting on it. We know that pressure is everywhere across here. So if I have a same pressure on the top and bottom in the vertical direction, I can't really have any gradient across that. And so this we know has to be 0 in this case. So that means that rho v squared over r is equal to rho g. So these rho's will cancel out, and we can write that radius of curvature is equal to v squared over g. And if we take this to be v squared, square root of 2gh, we know that should be 2g times h over g. And so for the way this works out then, the radius of curvature ends up being twice the height of the fluid that's stacked up above it. So as that interface drops, this radius of curvature gets smaller and smaller, and you'll get a tighter and tighter curve. And that's simply because it's in free fall as it comes out, and there's not any pressure gradient that can be supported across that. Okay, moving on then, we have the exit velocity, and we now need to relate that to the settling rate of the interface. Okay, so we have here V2 is the square root of 2gh. And we also had this relationship that dh dt is equal to minus v1. Or we can say that's equal to minus, and by our conservation of mass, we have that as AE over AT times V2. Or that's equal to minus AE over AT times the square root of 2GH. Okay, so this now gives us a differential equation that we can solve. We have an initial condition for it. It's a simple first order ordinary differential equation, and we can get the solution directly. So it's separable, so we can just separate that to dh divided by the square root of h on one side. And on the other side, this is going to be minus AE over AT times the square root of 2g times dt. And we're going to integrate that between our limits from both of these variables. So we start with an initial height h, and capital H, and it goes to some intermediate height. I could go to, actually we could just make it go all the way to 0. But we could make it an arbitrary height, little h in between. And then this is going to go from time t equals 0 to some arbitrary time t. So this integral over here gives us h to the plus 1/2 divided by 1/2, evaluated from capital H to h. And on the right-hand side, this is simply going to be minus AE over AT square root of 2g times t. Evaluating the limits here, we get this intermediate step, and we can finally rearrange this to look like this. So this is the ratio of the areas, square root of h minus h of t, so that's whatever the height is at a given function of time. You can invert that to calculate how h varies with time. It goes with t squared. Also in the second form that I have over here, I changed the cross-sectional areas into diameters, and I changed the area of the exit, where this was the effective area. I changed it to be the actual opening diameter times the contraction coefficient, which is from the vena contracta effect due to the nature of how the opening looks like. So this can be between about 0.5 to 1 depending on the geometry of the exit. Okay, so that is the end of this problem. There's not anything further I can think to add to it right now. I hope you found that helpful.